All right. Okay, what we were doing last time was we were looking at ordering in systems with a continuous symmetry, just as you can see there on the left-hand side of the screen. And what was special about it was the fact that it has an infinitely degenerate ground state. And what we saw last time, I'm not going to go through all the calculation, but what we saw was that there were two types of excitations. Ones which are where the amplitude of the order parameter changes, and that incurs an energy cost. And then the other was a change in the phase of the order parameter, the direction of the ordering, and that cost no energy. And then what we did was we calculated what was the energy spectrum of the different fluctuations. And what we found was that you get transverse fluctuations, which are gapless. And so as k goes to 0, those cost no energy, whereas the fluctuations which are longitudinal have a gap, even as k goes to 0. And so what we discovered then, that if you have ON symmetry, there are n-1 gapless modes and one mode which is an amplitude mode, which has a finite energy. So why is that important? Well, it's important because as you go down to low temperatures, the amplitude mode, that amplitude mode has got a finite energy cost to excite it. So that one is going to be frozen out as you go to low temperatures. But the phase modes, the directional modes, those can be excited because they don't have any gap. And we talked about modes which go to 0 as k goes to 0. We call them Goldstone modes. And we had a long discussion, and we realized that not every acoustic mode is a Goldstone mode. They're only Goldstone modes if they are a consequence of a spontaneous symmetry breaking. And we went through that in some detail. So then what we did was we went and calculated the correlations and the susceptibility of the system. So we wrote down our free energy, we found the order, and then we looked at the Gaussian fluctuations about the state of order. And we did that calculation. And what we discovered was that there are fluctuations which are longitudinal, fluctuations which are transverse to the order. And we then went and calculated the effective Hamiltonian, which you can see there on the lower left of the screen. And once we calculated that effective Hamiltonian, we can then read off the two-point correlation function in the longitudinal and transverse directions. And those are given by what you can see in the middle of the screen there. And what we discovered then was that the longitudinal correlations have a finite correlation length, but the transverse correlations have no correlation length at all. The correlation length is in fact infinity. And so what that means is that if you look at the longitudinal correlations, they are exponentially decaying. But as you go below TC, the transverse correlations are all power law decaying with distance. And that's true for all temperatures below TC. So that's where we ended last time. And then we made some remarks about the correspondence between what you do in statistical mechanics and what you do in quantum field theory. So in quantum field theory, if you have a particle that has a mass, the two-point correlation function, or the propagator, goes like 1 over k squared plus m squared. In statistical mechanics, the correlation function goes as 1 over k squared plus the correlation length for -2. And so we see there's a connection between the mass of a particle in quantum field theory and the inverse correlation length in statistical mechanics. And so the fact that we have an infinite correlation length, which is transverse in statistical mechanics, that means that those correspond to massless particles in the quantum field theory. Now that's all very exciting. That's telling us about correlations, and so we've seen it's very different when you have a continuous symmetry than when you have a discrete symmetry. Now we're going to talk about the emergence of rigidity, the emergence of order. And then what we're going to do is after that, we're going to look at what is the lower critical dimension for ordering when you have a continuous symmetry. And then lastly, we'll very briefly show you how you can have a topological phase transition known as the Kosterlitz-Thouless transition. So let's get started. And the section headings, I didn't put them in my notes here, so I'm not going to remember them, but they are on the web page, the Canvas page for the course. Okay, so let's get started then with with rigidity. So what is our goal here? What I want to show you is that rigidity in a general sense emerges from the spontaneous breaking of a continuous symmetry. I'm going to show it to you in the simplest context, but it applies well beyond what I'm going to be showing you. And so what this is going to end up being is it's going to be basically it's a consequence of the transverse power law correlations that we derived last time. So this is the observational consequence, the physical significance of this general result that we obtained through these fluctuation calculations. So how am I going to do that? Well, let's go back to our effective Hamiltonian, which we have over here on the left-hand side of the page. So let me write that out again for you, but I'm going to write it out in the following way. So what we have over on the left-hand side is what this looks like. Now, this part over here is the longitudinal part. That's the part that I just underlined. That's the longitudinal part, and we're not going to be interested in that. So I'm just going to write this down as the longitudinal contribution. And then I want to write down what the transverse part looks like. So the transverse part is the part over here. And G perpendicular, the transverse part, goes like 1 over k squared. So G perpendicular to the -1 goes like k squared. So if I were to write that down then in real space, what does it look like? Well, it looks like this. Okay, so this comes from simply taking the Fourier transform of k squared, phi perpendicular k squared, and so it looks like this, and this quantity r is going to end up being the rigidity. Okay, so let's see why. So let's have a look at what is the interpretation of this formula. So the interpretation is quite subtle, and this is where it all comes from. So here's our interpretation. So I want you to imagine that that I have a system going from say x equals 0 to x equals L, and now I've got the order parameter with some direction over here, and then some direction over here. So what I'm doing is this. I'm grabbing the system, like the spin at this end, and then I'm going along here, and the one at the end L, I'm rotating that way. Okay. Now, what does this formula tell me? What I'm doing is I'm keeping those spins. I'm just rotating them. So I'm changing the phase. I'm changing the angle. When I change that angle, that gives me a gradient of phi. It gives me an angle, a rotation of this spin relative to this one. And so it creates a term, grad phi squared. And so it raises the energy. So rotating this spin but keeping this one fixed, that then gives rise to a gradient of the phase squared. So let's draw in the phase. That gives you a gradient of phase squared. And so that means that gives you an energy cost. So that means that you feel a restoring force when you try to make this perturbation. And so this restoring force is exactly like a spring constant. And we can calculate what it actually is. So what is it? What is that restoring force? Well, we can just simply read it off from our formula. So over here, we calculated that the transverse correlation goes like m to the minus 2 times over k squared. So what that means is that when I plug that into this formula over here for r, what we see then is that this r is just equal to m squared. So remember that m is the magnitude of the order parameter. And then this thing over here is a rigidity. Why is it a rigidity? Well, it tells you the energy cost per unit length, per unit phase deformation. And so this thing is basically something like a rigidity modulus, like a shear modulus or a Young's modulus or something like that. So, but it's the spin analog of that. So we've calculated this, and this calculation is true in Gaussian theory. So this is true only in the Gaussian approximation, because we did the calculation for the fluctuations in the Gaussian approximation. So what you can see then is that if m is equal to 0, in other words, you're above the critical temperature, that implies that there's no rigidity. And if m is non-zero, i.e. T is less than Tc, then that implies that there does exist rigidity. And this rigidity it comes from the transverse part. So let's have a look at some physical examples of this. So let's talk about the magnetic example first. So you might have, for example, a Heisenberg magnet. So if I've got a Heisenberg ferromagnet, my picture looks very similar to what I was just drawing before. Something like that. So this thing is meant to be some kind of spin wave. And what is the rigidity that we've just derived? So the rigidity that we've just derived is known as the spin wave stiffness. It tells you how stiff the spins are. If the spins really want to line up, then to rotate them at that amount costs a huge amount of energy. So it's very stiff. If, on the other hand, the spins are kind of floppy, they're not very stiff, then it won't cost a lot of energy. And so that thing is called the superfluid stiffness, the spin wave stiffness. Then the next example I want to give you is a superfluid. And what we're not going to go into this in great detail in this class, but I want you to imagine that we have a superfluid. So this is a Bose-Einstein condensate. In other words, a macroscopically occupied wave function, macroscopically occupied wave function. 10 to the 23 helium atoms are all described by the same wave function. Okay, so that's not something that normally happens. So let's write down that wave function as psi of r, and we can write down that wave function as its magnitude times e to the I phi, some phase. And now we can say, well, if that phase varies in space, like so. Okay, so then this is a configuration where the phase varies in space, and you can call that excitation a phonon, if you like. Sometimes people call it that. And what is the R? Well, the R in this case now is the rigidity of the order parameter. So this is called the order, well, not the order parameter rigidity, wave function rigidity. And in the context of superfluids, this is known as the helicity modulus. So why is it called that? I haven't taught you very much about superfluidity, but let me just tell you a few facts, and so you can see where it comes from. So in a superfluid, there is a superfluid velocity which is irrotational. I'll explain what that means in a minute, and that is the property that means that that this simulates having no viscosity. And I will show you very briefly a little bit about that in a later lecture, but not today. So I want you just to take for now the fact that if you have a velocity field that we'll call the superfluid velocity, so if this thing is equal to 0, this thing means that you essentially get something that you might call no viscosity. It's not really true. It's not actually no viscosity. It just means that you just don't get any resistance to a shear. So when you measure it, you would measure the viscosity to be zero, but it's not really true that the viscosity itself is zero. It's just that the actual resistance is zero. And so you would interpret it as if it was zero viscosity, and that's what a superfluid is. So where does this come about? So this will I can show you later, but how this happens is in a superfluid, the velocity turns out to be the following. It turns out to be h bar over m times the gradient of the phase of the wave function. So this is the so-called superfluid velocity. And so why is this interesting? Well, suppose I've got a superfluid, then you might say, well, what is its energy? So its energy is going to be just a half rho v squared integral over volume, like so. So that is the total energy of the superfluid, just the kinetic energy. And then given this this identification, then what it ends up looking like is 1/2 the integral over space of this rho times h bar squared over m squared grad phi squared. And so this quantity here you might call the density of superfluid. And you can see that this thing is behaving like a rigidity. So you can think of this quantity here is like the rigidity. The density of superfluid is a modulus, and it's called the helicity modulus because it's telling you about the modulus, about how you can make changes of the phase of the wave function. So you can think of that as being some helical structure in space, and so it's called helicity. So that's the superfluid density is actually a modulus. So superfluids have a weird kind of stiffness, a quantum stiffness that is what's responsible for their properties. Here's another example. So you might have a look at an elastic solid. Okay, so what's an elastic solid? Well, you have, say, let's make it a crystal like this. So here are your atoms. The atoms would be ideally in their lattice positions, but in a crystal, what happens is you deform it, and as you stretch it and deform it or bend it or whatever, you move the atoms from their equilibrium positions, and then you observe that there's some restoring force, and that's what you measure as a modulus. So what you actually have is when you deform a solid, so a deformation gives rise to an atom being displaced from its equilibrium position. So we'll call that displacement U, and it depends on which atom you have. So how do you quantify that? So again, I'm not going to go through the theory of this, but the theory of elasticity looks at how the displacement varies in space. So let's think about why that would be. Suppose I've got all the atoms and they're all displaced by the same amount. Is there going to be any restoring force or anything like that? No, it's just the shifting. That's just a global translation. If, on the other hand, they're shifted in a way that varies between one atom and the next, there's a spatial variation, then that's going to cause a cost in energy. So there's going to be an energy cost to make deformations in space that are not uniform. That's the basic idea. So what you end up writing down is a thing called the strain tensor. Sorry about that. That just means that there's a fire, but it's a long way away from here, so you don't have to worry. So the thing is the strain tensor. So we write it like this: Uij of R, and what is this thing equal to? In a linear approximation, it looks like this. So it looks like this. So what I do, so I and J go from, say, X, Y, and Z, or if you like, 1, 2, and 3. And so UI is the component of the displacement, and what we do is we construct a tensor. We're looking at how does the displacement vary in space. Space is a vector, displacement is a vector. So therefore we have in general a tensor, and the appropriate tensor turns out to be the strain tensor, which I've shown here. And then if we work out what is the free energy of the system. So let me write down what the free energy is. So the free energy is the integral over space of some scalar quantities, which I can make from the strain tensor. So the free energy is a scalar, so what quantities can I make? Well, I could take the tensor, or the matrix Uij as a function of space. I could to square that, that would be a scalar, and then I can multiply it by a coefficient, and that coefficient is conventionally written as 2 mu. And then there's the other thing I can do. Can anybody think of what other scalar quantity I can make out of the strain tensor? Trace. I can take the trace, exactly. So the trace of a matrix is the sum of the diagonal elements. So I do UKK of R squared, and then the coefficient that goes in front of that is called lambda, and then I have this as my free energy. Now this is true for a mythical isotropic solid. Something that has some crystalline symmetry, you'll have to write down these scalars in terms of the irreducible representations of the group symmetry. So we're not going to do that here. So this thing over here, this coefficient is called the static shear modulus. And this thing over here is called the Lamy coefficient. But they're just phenomenological parameters that depend on microscopic interactions and potentials and things like that. And we don't really care where they come from. We know that they reflect some underlying microscopic physics, but they are the moduli that come from this more complicated free energy. So this Landau free energy is the basis for elasticity theory, and it has the same, the moduli have the same origin as what we just showed you for these more for the ON model. All right, so let's let's ask another question. So we've seen that the rigidity, in fact, goes like the order parameter magnitude squared, at least in our theory. And so we know that how does the rigidity scale? How does rigidity emerge below TC? So, well, you might say, well, that's pretty easy because we know how the magnitude of the order parameter goes. The magnitude of the order parameter goes as minus t to the power beta when t is less than 0. And we know that in mean field theory, the order parameter grows with the square root power. Okay, so that's just showing you this. So here is the magnitude, here is t, here is tc, and then the order parameter goes up like that, or on the other side, it goes like that. So it's forming a parabola at tc, and so therefore it's going like the square root around this thing here. So here, this is m, this is a parabola. So that means that the beta is equal to 1/2. That's a square root power law. So then if we buy that, then what it means is that the rigidity is proportional to m squared, which like equals m squared, and so therefore it's going to go like minus t to the power 2 beta, and that would be 2 in this particular case. So that's what you might think is how the rigidity scales as you go below the critical point. Let me turn this off, but it's actually not quite correct. So let me turn off the fire alert. Okay. So why is it not quite correct? Well, even if you haven't been to the previous class on phase transitions, I can quickly show you using dimensional analysis why this isn't correct. So this is as they say in Russian, not quite correct. So why? Well, if you look at the dimensions of the free energy per unit volume, so those dimensions go like L to the minus D. So this is the free energy over kT per unit D. And the length scale that we're going to be using here is the correlation length. So this is going to scale then like the correlation length to the power minus D. So then if we compute what does grad phi squared transverse phase look like? So this also has to go like L to the minus 2. And so that means it goes like psi to the minus D. So the phi is dimensionless, it's just an angle. So the grad has got dimensions of 1 over length. So grad phi squared is going to go like L to the minus 2. So that's going to go like the correlation length to the minus D. And so what that means is that when I compute the free energy, so the free energy per unit volume is R grad phi perpendicular squared. So that means that the dimensions of R go like L to the power 2 minus D, which means it goes like psi, the correlation length to the power 2 minus D, and the correlation length goes as T to the minus nu. So this goes as T to the minus nu times 2 minus D. So the rigidity scales in a very different way than what we found, or does it? Okay, so it seems that the rigidity scales like t to the power nu to the 2 minus d, which is not equal to t to the minus t to the 2 beta. So, but we can see how it's connected to it. So we can see the connection using scaling laws. So I'm not going to derive this, a scaling law from phase transition theory. And that scaling law, alpha plus 2 beta plus gamma is equal to 2. And this alpha tells you about the heat capacity divergence. Beta is the order parameter emergence. This one is the susceptibility divergence. And there's another scaling law which says that gamma is equal to nu times 2 minus eta. So gamma we've already just described. Nu is the correlation length divergence. And this eta here is the anomalous correlation function scaling. So that tells you that the correlation length at Tc scales as k to the minus 2 plus eta. So that's one that we also derived last quarter. So if I put those two things together, include these two things, what you can show then is that R then scales as minus t to the 2 beta minus nu times eta, and that's true for t less than 0. So what we derived just by a very simple argument just now, using Gaussian mean field theory, that we derived that the rigidity is the order parameter squared, and that's what I derived for you at the beginning of the lecture. And then this term over here is a correction that comes from non-Gaussian fluctuations. And the reason that we were able to do that is because this scaling law, these are exact identities which can be proved by the normalization group. Okay, so now we've learned how order emerges, and now what I want to discuss then is what is the lower critical dimension of systems with a continuous symmetry. So when a system with continuous symmetry orders, then it gives you some sort of rigidity. So now we want to ask, what is the lower critical dimensionality? So we saw at the beginning of this class that if I have a system with a discrete symmetry, that if I'm in one dimension, I do not have order. If I'm above one dimension, then I can have long range order. So now we want to ask, is there an analogous theorem for systems with a continuous symmetry? And so I'm going to show you that there is, and I'm going to show it to you in two ways. So first of all, I'm going to do you a very sloppy calculation. I'm going to show you that the reason that you don't get order is we're going to see that there's dangerous fluctuations, and those dangerous fluctuations are long wavelength phase fluctuations that destroy order. And I'm going to show you that as a divergence in computing a correlation function. Then I'm going to directly compute the order parameter for you and show you by direct calculation that its value is equal to 0. So we're going to answer this in two ways. So first, by exposing a divergent aspect of correlations. And then second, by directly computing the expectation value of S and showing you that it's actually equal to 0 in a particular dimension. So let's do the first way first, and that's going to basically tell us immediately what is the lower critical dimension. So remember what the strategy was for the lower critical dimension. The strategy is to identify the dangerous fluctuations that destroy a ordered, or in this case, a rigid state. So just as we did with the discrete symmetry, there we saw that flipping individual spins didn't make any difference, but flipping a finite fraction of the spins, that was a dangerous fluctuation and caused the free energy to be minimized by having a whole system full of domain walls. So we can ask what is the most dangerous fluctuations here, and we already know the answer because I already discussed it in the last lecture. So we know that the most dangerous fluctuations are the ones that are easiest to excite. And so in the case of a system with a continuous symmetry, these are the transverse or phase fluctuations. So let's have a look then at the two-point correlation function for the transverse, the transverse fluctuations. So here it is, the two-point correlation function. So we've already calculated it because that was how we ended last lecture and how we began this lecture. We began today's lecture by writing down the free energy over here on the left-hand side. And where did that come from? That came from the calculation that we did last time, where we literally wrote down the effective Hamiltonian for the fluctuations about the mean value shown here over on the left. So we know that the two-point correlation function for the transverse fluctuations goes like this. It goes as the magnitude squared, then it goes like the integral over 2 pi to the d, and then e to the I k dot r minus r prime, the Fourier transform, times the inverse of the two-point correlation function. So that gives us a factor of 1 over k squared over here. So that's what the transverse correlation function is going to look like. And we need to put some limits on this integral. So let's put the limits on it. Well, we know that when we're writing down these theories, they are coarse grained. So at the upper limit, they have a coarse graining scale, which is lambda. So that tells you the scale below, above which there are no Fourier components. And then we have we're going from k equals 0 to k equals lambda. So we have the lower limit being 0. So this lambda here is the coarse graining scale, just to remind you. Like so. And so the question we want to ask is this integral finite? So we want to find out if it's finite. So the way we're going to do this integral is we're going to do it in k squared is rotationally symmetric in k space. So we can do this by doing it. It's a spherically symmetric integral. In d-dimensional space, k space, of course. So I can write this then as the G perpendicular, apart from a factor which is the surface area of a d-dimensional unit sphere. So we'll call that SD. It's going to be that times the integral from naught to lambda k to the power d minus 1 dk over k squared e to the I k dot r minus r prime. Like so. So now we can see that there is a problem. And we can see that there's a problem at the lower limit. So let's have a look at the lower limit. So what do we have? Integrand is going as k to the d minus 1 over k squared, which is k, it's not twiddle, it's equal to k to the d minus 3. So I've got to integrate it and then see if it converges. So what you can see straight away is that if d is less than or equal to 2, then at k equals 0, the integral is divergent. And because this is an integral as k is approaching the lower limit, we call this an infrared divergence. And in fact, in d equals 2, it's logarithmically divergent. So if I put d equals 2, then I've got k to the 2 minus 3 is k to the minus 1, integrated and then evaluated at k equals 0. So the integral of 1 over k is the logarithm of k, and then I set k equal to 0, and so I get a logarithmic divergence. So at d equals 2, it's logarithmically divergent. If d is less than 2, then it is power law divergent. And so what I found then is that I do not get, the fluctuations don't converge for d less than or equal to 2. And so that suggests that in order for them to be finite, the correlations of the fluctuations have to be finite only for d greater than 2. And so that then suggests that systems with a continuous symmetry only order for d greater than 2. And so that means that the lower critical dimension is 2. Okay, so that is the result, and now I want to do the next thing I want to do is I want to compute this directly. To show you it in a way that is more straightforward. So here it's a very sophisticated way of saying it. We're saying we're looking at the correlations. We see that the correlations of these logarithmic divergences, the correlations of these logarithmic divergences, how can the fluctuations be small and finite? And so that's the argument for the destruction of long-range order. Now I want to show you it by explicitly calculating the order parameter and showing you that it is equal to 0. So we're going to do that first, and I want to make one other comment here before we get into that. So the comment is this. I can make a computer simulation of something completely different, not a superfluid and not a magnet. I can make a computer simulation of fish or some animals diffusing around in 2 dimensions, and they can follow each other and form a flock or a swarm or a school. Okay, and you can make a simulation of that in 2 dimensions, and you will see that you'll get perfect order. You'll be able to see the fish swimming like this in some way, and it'll look very ordered. So there's a comment here, is that if we observe organisms, say swimming in 2D, it could be bacteria, they could be fish, whatever. It could be birds. They form a flock. And can have long-range order. You can see them swimming like this, and so you say, well, is that a violation of this theorem? So this theorem has a name, by the way. I didn't say what it was, but why didn't I tell you what it is? So this theorem is sometimes called in condensed matter, it's called the Mermin-Wagner theorem. And in high energy physics, it's called Coleman's theorem. Okay, so let's ask ourselves this following question. So you can have creatures which are self-propelled, swarming and forming a flock. So it seems to be that they proved that this theorem doesn't work. So is it? What do you think about that? So say it again. I heard you say finite size. So finite size means there's a minimum k, and so you never get to k equals 0, right?
Or I guess.
Right. Yeah, yeah. So you never get there, so you never see the divergence. That's a good argument. That's actually a good argument, and it's the reason you're right. That's the reason why you can have superfluidity in 2 dimensions. So the answer is so my answer to that is yes. In fact, this is roughly why we can make very thin, in fact, monatomic films of superfluid. So the theorem says basically there's no superfluidity in 2 dimensions, there's no superconductivity in 2 dimensions. It's not true. People spend their whole career studying it, but they always study it in a finite system. And if you had a system that was as big as the universe, it definitely would not be superfluid. So some of these effects are effects that only kick in at the size of the universe. Okay, so they may be academic, but I can make my organisms do this in a much smaller system than this. So this isn't the reason what's happening in these other systems.
Just a question about this finite size thing, but you will never see a phase transition.
You never see a phase transition in a finite system anyway. That's right. That's right. That's right.
But like the Mermin-Wagner theorem, like requires finite range.
It requires finite range and it requires an infinite system. So we haven't, strictly speaking, violated it if you have a finite system.
Yeah, but like if you have an infinite system, birds do not have finite ranges if they're moving.
Well, when a bird is a flock, the bird is following the bird in front of it. So they have a finite range interaction. Okay, I've got a flock, so I'm a bird, I'm swimming around, I'm a fish. So I'm basically following or trying to follow the birds in front of me in my neighborhood. So the birds do have local interactions. So the organisms do have local interactions. So they should be subject to this theorem. So there's one other thing. There's one other thing that nobody's brought up yet. I bet Cindy knows it. Because you were asking me about it, something related to this at the beginning of the class. What were you asking me at the beginning of the class?
Asking about the paper.
Yeah, right. And do you remember anything more about that paper? Okay, all right. So you just knew the paper. Okay, all right. Okay, so half this class are biophysicists. Well, non-equilibrium, yes, exactly. Okay, biophysics equals non-equilibrium. Okay, we assumed everything was in equilibrium. We assumed a Boltzmann distribution to do all this. Okay, it's not true. It's not true for these things. So the organisms do have local interactions, but they are not in equilibrium. In real life, of course, they're heterogeneous, you're right. But if I was just doing a simple computer model, I would just say they all have the same rules and do it like that. So it's not a question of the heterogeneity. It's a question of them not being in thermal equilibrium. So what that means is that when I write down equations of motion, I can write down terms there that I wouldn't that I wouldn't have if the system was in equilibrium. So in homework 2, so you have one of the questions. One question is to do what I did in class last week, to compute the fluctuations below TC. But the second question is to then try to apply a kind of version of Landau theory to look at a non-equilibrium system, looking at a non-equilibrium interface dynamics, excuse me, and working out the dynamics of that in the same spirit that we do for Landau theory, but now not writing down a free energy, but writing down an equation of motion. So because they're not in thermal equilibrium, what you do is you write down an equation of motion, and you can look at all the terms. I'm not going to go through that, but I think in one of the lectures I had a picture of a snapshot from Toner and Tu's paper. That's the one that Cindy was talking about, and there's a very complicated equation that describes the behavior, and that equation is not in thermal equilibrium. In particular, it violates the principle of detailed balance. And because it violates the principle of detailed balance, it's not subject to the Merman-Wagner theorem. Okay, so that's all I want to say about that for now. I'll take one more quick question.
So in the paper by Donor 2, like they make this argument that like the difference between XY and our model is the convective term. And if you think of it like the frog in Lagrangian coordinates, you have long range order because the birds can slip past each other, and like one bird can like interact with somebody like very far away.
I don't know if I buy that as the argument.
Like yeah, that's what they like say. I think when they in the paper.
I don't know. Let's not get into that.
Yeah,
Good topic for somebody to give a class lecture and term paper about. Okay, let's not. I want to do a bit more. So I want to do the next calculation. So it's interesting where it all goes wrong, and yeah, there's a lot to say about that, which if you get me started, it'll be a whole other lecture, and it'll screw everything up. Okay, so let's so what I'd like to do now is I want to now go ahead and demonstrate that there is no long range order in 2D. Okay, so that's the next thing. So we already suspect from looking at the infrared divergence that there isn't long range order. So let's see if we can calculate it. So what I'm going to do is we're going to take the ON model. I'm going to take n equals 2, and I'm going to take spatial dimension d equals 2. So that's called this is the 2D XY model. So let's have a look at what the order parameter looks like for the 2D XY model. So in the 2D XY model, I have S2 and S1. I've got two components. I'll call them S1 and S2. The order parameter could be, say, like this. So here is the vector S, and there is an angle here, which I will call theta, and we're going to make the order parameter have a unit magnitude. So we can think of S1 as being like X and S2 as being like Y. So that's why it's called the XY model. Okay. So we're going to write down the order parameter is the order parameter is let's see, S is SX. So I changed my notation in my notes. Bad idea. Let me try not to confuse you. SX and SY. So it's a two-dimensional vector like that. So I propose to compute the X component of S. So I'm going to compute the expectation of SX. And SX is just the expectation value of cosine phi. What's phi here? Phi is this angle. Okay. I call this theta, but I meant phi. Okay, so I'm going to compute the expectation value of that angle. And so that's the thing we want to compute. And I don't really like computing the expectation value of cosine. So I'm going to just compute the expectation value of e to the I phi and then take the real part of that. So we're going to take the real part of what? So I'm going to compute the expectation value. So that's going to be the integral, the functional integral over phi, e to the minus beta times the Hamiltonian, e to the I phi, and then I'm going to divide that by the partition function z. And so that's just the expectation value of cosine phi, and I'm going to call this number e to the minus w. So I'm going to define w to be that, and w it's called w because this thing is known in solid state physics as a Debye-Waller factor. So I'm going to just call it w. You don't need to know what it means, but we're going to just go ahead and compute that. Okay, so that's our goal, compute this object. So how do we do the computation? So we're going to do this at low temperatures. So T is going to be much less than Tc. And so when T is much less than Tc, the amplitude fluctuations can't be excited. And so if they can't be excited, we will see that they're frozen out because they have a gap, an energy gap. And so what that means is we only get the transverse modes, as we've talked about several times now. So what that means is that for my Landau free energy, I'm just going to write that in the way that I did for my superfluid at some rigidity, and then the integral of grad phi squared integral ddr. Actually, this is fine. This is fine. Nobody's confused. So I'll just leave it like that. And this d is equal to 2. So this is that's what our Hamiltonian is, our effective Hamiltonian. Okay, now the thing that we are computing, so what I want you to notice is that this Landau free energy is a quadratic free energy in terms of phi by construction. So when we are computing, so what we're really computing over here is we're computing the expectation value of e to the I phi. Right, that's what we're computing. Cosine, basically what we're computing is the expectation value of cosine phi. So we're computing the expectation value of e to the I phi and then taking the real part of that. So we're going to use a result from Gaussian integrals. So we want to calculate the expectation value of e to the I phi. And what is that? Well, if you have if this expectation value has a probability distribution, which is something like e to the minus phi squared over 2 sigma squared over 2 pi sigma squared square root, for example, if you had something like that and then did the integral, so this is a Gaussian variable, then what that means is that the expectation value of e to the I phi, you can just do that as a Fourier transform, and that is equal to e to minus 1/2 the expectation value of phi squared. Okay, so how many people have seen that result before? Oh, nobody. All right, no problem. So all you have to do is you can check this by doing this integral e to the minus x squared, take its Fourier transform. And you know that this integral is basically going to go like e to the minus k squared, something like that. So we're just basically doing that Fourier transform. Okay, so check this using something like that, and you'll see where this comes from. So I want to just take this little result here, and then go ahead and compute it. So it's a very useful thing to know. So what that then tells you is that our quantity W is then just 1/2 the expectation value of 5r squared. And what that is then is equal to G perpendicular at r equals 0. So now we need to compute what that is, and we can just simply write that down as the integral d dk over 2 pi to the d, and then e to the I k dot r minus r prime over k squared evaluated at r equals r prime. So that's what this thing is, and this integral is the thing that I did for you, 10 minutes ago. And so what we know is that if I've got this in d equals 2, we know that this integral diverges. And so that means that w goes to infinity. So the Debye-Waller factor goes to infinity. So what that means is that when I compute Sx, that is equal to e to the minus w is equal to e to the minus infinity is equal to 0. So that's the x component is equal to 0. There's nothing special about the x component. I could equally have done this with the y component. So the same thing is true. Expectation of sy is also 0. And so what I conclude is that both components of S have expectation value equal to 0. And so now I know that expectation of S is equal to 0. And so that's true, then I've just shown you that there is no long range order in d equals 2. Okay. All right, so what I want to so is this conclusion correct? Well, the conclusion was believed to be correct for many years, but it's not true. It wasn't in 1974 or so. Costas and Thalis showed that this is not true, and the reason is this: it is everything I've shown you is exactly true. It is absolutely true that S is equal to 0. The thing is this: not every phase transition has to have a non-zero order parameter. Okay, why? This is an order parameter that is local. So this does not mean that there is no long-range order in 2D. It only means that there is no local order parameter which is non-zero in 2D. And what Kosterlitz and Thalis proved Actually, I should call it the Berezinski-Kosterlitz-Thouless transition, because it was also anticipated by Berezinski as well. So let's call it the Berezinski-Kosterlitz-Thouless transition. So what they showed is that, in fact, you can have a topological phase transition. Where the order parameter is non-local. Why non-local? Well, if you have something that is topological, what that means is that you go around the trajectory, come back to where you started, and you find that something has changed by 1 or by an integer. And that's called, and that is a topologically conserved quantity. And we'll talk a little bit about those, not today because we're out of time, but later. So let me give you an example of that. Okay, so I'm going to give you a quiz question. Okay, we're going to finish this part on Thursday, but here is a quiz question. Okay, so I have a hunter. Okay. Okay, so it's somebody with a gun, right? So this hunter does the following. He starts off somewhere, so he goes south, and then east, and then north, and then west. So he does that, south, east, north, west, okay? He finds himself, and he's doing this by 1 mile. 1 mile south, 1 mile east, 1 mile north, 1 mile west. Then he finds himself not where he started. He shoots a bear. And the question is, what color is the bear? It's white. Why is it white? Huh? Wait, what? The color of what? Huh? I didn't really hear what you were saying.
Because you are using the pipes.
No, my color is blue, actually. Yeah, you want to see white? Here's white. Okay, that's white.
I think
Yeah, it's not. Look at it. Well, that's because of the crappy projector. Okay, what color is the bear? It's white. Okay. Okay. So next time we will discuss why that's true. Okay. Okay. All right. So thanks. Let's turn off the recording and